We'll input images from the Mnist dataset. This is a dataset consisting of handwritten digits from 0 to 9. After inputting the image, we will perform a convolution. We'll use two filters, or kernels as they're called, that have the dimensions 5 by 5 by 1. The activation function, denoted as A, is ReLU. Next, we'll perform max pooling with a pool size of 2 by 2 and a stride of 2. This is our first layer. Then, we move on by performing our second convolution. This time, we'll use 4 filters that have the dimensions 3 by 3 by 2. The activation is sigmoid. We'll then perform max pooling exactly as earlier before we flatten the matrices out. This gives us a flattened layer with 100 nodes. Here is our second layer. Finally, we have a fully connected dense layer which outputs our predictions. Without wasting any more time, let's see the model in action. We start with the input layer, which is a 28 by 28 by 1 dimensional grayscale image. The image is fed into the first convolutional layer that consists of 2 5 by 5 by 1 dimensional filters and 2 biases, one for each filter. We'll use a stride of 1 and an activation function called ReLU. We start with the first filter and map the activations onto activation 1 in the first layer. Then we do the exact same thing for the second filter and map the output onto activation 2 in the first layer and move on. As you can see, the first convolution outputs 2 different images, or matrices. These are called channels. Next up is the max pooling. We'll use a pool size of 2 by 2 and a stride of 2. We run the pooling for each of the channels and output them respectively. The idea is that we want to extract only the most activated pixels from the first convolution and shrink the dimensions. As you can see, we have shrunk the dimensions from 24 by 24 by 2 into 12 by 12 by 2. Have a go and count the pixels if you'd like to. Next is the second convolutional layer. Here, we'll use 4 filters with a stride of 1 and an activation function called sigmoid. As you probably noticed by now, these filters are stacked, and if you separate them, you'll see that we actually have 8 filters. So, what's going on? Well, there are 4 filters with the dimensions 3 by 3 by 2. Since we have 2 channels from the previous activations, we'll have 2 channels in each filter. In addition, we also have 1 bias for each filter. Running the convolution will return 4 outputs, 1 for each filter. As you can see, we kind of lose the idea of what the original image was. From this point on, it's hard to decode what is actually going on. But let's continue to the last max pooling. We'll do exactly as we did earlier. Since there are 4 channels, we'll output 4 channels. What we extract is the most activated pixel values from each channel. We'll then take these 4 matrices and flatten them out so that we separate each and every pixel. We went from 4 matrices that were 5 by 5 to 1 flat layer with 100 nodes. To make the visualization easier, we'll shrink the nodes so that we only see the first 5 and 5 last nodes. Finally, we have the output layer, where we want to output 1 out of 10 different predictions. This is a fully connected dense layer. Running the activations from the 100 nodes, we see that the model predicts that the inputted number is 7. This is exactly what my brain told me as well. Crazy, isn't it?